Started. Got it? All right, let's begin with a word of prayer. So, Heavenly Father, we thank you for today. Again, Lord, I thank you for your creation, that we can understand it. Thank you for math. Thank you for these students. I just pray that you be with us today. Help us to glorify you, Lord, and we do. In your name I pray, Lord Jesus. Amen. Okay, so without further ado, a couple of examples or a comment, correction. I don't know. So if I wanted to do something like calculate integrals over this solid. So here we have x plus y plus z equals to, let's say, 1. And I want to calculate and say also x greater than or equal to 0, y greater than or equal to 0, z greater than or equal to 0. Let's call all of this t. All right. The set of x, y, z, which satisfies those bounds. Right? So it's bounded by the plane x plus y plus z equals 1 and the coordinate axes. I want to describe how to set up triple integrals over such a region. So the advice I'm going to give you today is a little bit kind of backwards of what I did last time. So here's it is. So suppose I want to integrate over this region T some function of x, y, and z. All right. So there's different ways to set it up, right? But basically what I'm going to advocate here is that we think of just pick one of the three dimensions and try to project it out. So the simplest thing to do probably is to project out the third dimension, the z. So in the z, the top is this, right? And the bottom, of course, is the that down there, right? And the top projects down onto the bottom, actually, right? So the projection in the xy plane of t is just equal to what? It's xy such that what? Well, I can draw a picture of it easier than I can write this set. Basically, the picture is something like this. If this is x and this is y. So here's the projection is this. So you could capture this a couple different ways. You could write it as a type 2, or you could write it as a type 1 region. Tell you what, I'll write it as a, I don't know, let's see here, how about 0 less than or equal to y less than or equal to blank, 0 less than or equal to x less than or equal to 1. So what's y between? If you look at like here. So down here is 0, right? Up here is y equals to x. So you have 0 less than y less than x. So, yep.
At the origin, it's 0. Wouldn't it be 1 minus x?
Oh. Thank you. Oh, I'm an idiot. Let's see here. 1 minus x is, of course, that line, yeah. I'm thinking of something else. This should be 1 minus x. Very good. Very good. Now, of course, the way to see that this blue line right here is what? Like, if you don't see this geometrically, how could you discover it algebraically that this is the blue line? What is that? That's where z is equal to 0, right? That says what? That says that x plus y plus 0 is equal to 1. Therefore, y is equal to 1 minus x. See, that's why that's the top curve there, right? But you have to see in your mind's eye the projection of the solid onto the triangle, right? I can't, well, I mean, I suppose I could, but let's just say that that's a geometric step. So once you have this clear projection of the third dimension, z, onto the triangle, then I can set up the integral. Let's see here. So the most complicated one is the one that comes first. So this top is what? Z equals what? 1 minus x minus y, right? So I go 0 to 1 minus x minus y. That's the z bound, right? And then what comes next? Yeah, 0 to 1 minus x. That's the dy. And then 0 to 1 would be the dx. And then, of course, I still have, don't let me forget, there's a function in here, right? That's just there, it rides along, right? And then you iterate these integrals like we did with the double integrals the other day. The difference in logic here is I'm saying pick a dimension that you want to project out, smush it down, and then see where that takes you, all right? The viewpoint I was advocating Thursday was to look at it always three-dimensionally. Every bound I was looking at three-dimensionally. My point to you is you don't need to do that. Once you suppress one of the dimensions, it becomes a two-dimensional problem, and you can kind of work your way that way. Let me do this a different way. So what if I wanted to, what if I was instead looking for the integral like this? You guys pick an order. I'll work it out. dx, dz, dy. Okay. So if I'm looking to integrate something like that, that means that I'm projecting out the x direction first, right? So x is going to have the complicated bounds. Basically, I want to look at a projection along the x-axis. So I want to understand what's the projection onto the yz plane of t. What is that, right? So here's a picture of it. Maybe I shouldn't put equals here. It's kind of bad form. It looks like this. So you can see it, right? If you imagine projecting, if you look at the x direction, this shape always is what? Of course, the plane is the first thing you hit. I mean, well, it's the last thing you hit. It's the positive. And then you've got the yz coordinate plane, right? So if you look at this, you can see that 0 is less than or equal to x is less than or equal to that, right? Which is what? 1 minus y minus z. So I've got 0 to 1 minus y minus z as my innermost bound. But more important than that is once I make that choice, then what remains is a lower dimensional problem. It's a two-dimensional problem. The question is then what's the projection of the solid onto the yz plane now? It's just this thing, right? It's again one of these deals. Now the question then remains, how do you want to characterize that triangle in terms of y and z? Well, if we do y last, that means I have to make the y bounds kind of boring, right? So I have 0 less than or equal to y less than or equal to 1. So the ones that captures the triangle-ness of it, if you will, blank less than or equal to z less than or equal to blank. How do we fill in the blanks? Well, as I've drawn the picture, we should think about here's the top z, here's the bottom z for a fixed y. So of course, I've got 0 below, and this line is what? Yeah, z is equal to 1 minus y, right? Now, just to emphasize geometrically where that's coming from, that's precisely the line, this line right here, in the larger solid. See that? Which is where x is equal to 0. When you put x equals to 0 into the plane equation, you're left with y plus z equals to 1, which of course reduces to z is equal to 1 minus y. So I have 1 minus y as my upper bound here, and then the triple integral becomes 0 to 1 minus y and 0 to 1. Now, one of you was trying to tell me when it was Thursday, you were trying to tell me I could find the next answer from the first one from the XYZ symmetry. I should have listened to you. That would have probably been an easier way to do it. The problem we were looking at actually had like an XYZ exchange symmetry. Maybe this one does too. Let's see. I think that may be the case, right? What's the difference here? Anything the same? Let's see. It's like z goes to x, y goes to z, x goes to y. Is it the same here?
Yeah.
X goes to y, x goes to y, y goes to z. Yeah. It doesn't have to work out like that. That's a quirk because of the constraints all being symmetric. You have x greater than 0, y greater than 0, z greater than 0. X, y, and z could be interchanged and you don't have any difference. And the same for the upper bound. So this is a very symmetrical problem, which is why the answer you could see just from an argument of symmetry. But I wanted to show you how to think of it in terms of taking the three-dimensional solid, projecting onto one of the coordinate planes, and then going from there. Any questions? Do you see the distinction in philosophy between what I was saying this time and what I was saying last time? Last time I was always saying look at three-dimensional space and try to pin it down by looking at three-dimensional space. Now I'm telling you, once you compress that first dimension, you're left with a two-dimensional problem, which you can draw a nice, concise picture for, and you don't have to draw three-dimensional pictures to figure out the last two bounds, which is where we made the mistake last time. Although some of you weren't here, so you're saved from it. Actually, many of you were not here. It's okay. Was there some kind of party I wasn't invited to or something? The Chick-fil-A opening? Oh, physics test. During my class? Right before? Oh, so you're recovering from a physics test?
Some of us came after it.
Oh, okay. Tell you what, let me work another problem that is considerably more difficult than this one, and then we're going to move on, all right? So here, I'm going to let T be the shape which is bounded. It's bounded by y is equal to 4 minus z squared, and y is equal to the absolute value of x. I'm completely focusing on the bounds today because honestly, the integration you guys can do. The bounds, that's the trouble. So I want to understand what is this shape and how do you calculate its volume? All right. Now, if we understand how to calculate its volume, we can easily calculate volume integrals with respect to this shape as well. So how do you understand what this looks like? What do you do? What I do is I look at lower dimensional pictures and try to, yeah? No?
We know what the absolute value of x looks like. Does the fact that we have two equations both equal to y in this case mean they have to be equal to each other?
Well, let's see here. So let me draw a couple pictures. First of all, I'm going to draw a picture. It's kind of a little bit weird. Well, like this. Here's x, here's y, right? So absolute value of x would look like this, right? And, here we have x equals to y. Here we have x equals to minus y. And you could draw this picture for any z, right? So it's basically a pair of half planes that meet at the z-axis, and they just go up and up and up and down and down and down, right? Two vertical half planes joined at the z-axis. That's what y equals absolute value of x is. Do we agree? That we can understand. And the other one, z, y, and I know I'm kind of drawing these weird, but you can deal. Something like this, right? I mean, it goes on and on, but. So this is y is equal to 4 minus z squared. So if I draw it this way, it's a sideways opening parabola, right? Or if you like, this bottom curve is z is equal to the square root, well, minus, right? Minus the square root of what? 4 minus y. And the top curve, or they're both the top and the bottom you can express as 4 minus z squared equals to y, but the top is a positive square root for z, and the bottom is the minus square root for the 4 minus y function, right? Right, that's the question, is what is the, so you have two cylinders, right? I mean, they're not, I mean, I guess one's an infinite wedge, right? Goes up and down. And the other one is this parabolic cylinder, which, I mean, I can try to draw them in separately. This one is something like this, right? Whereas this one, I'm not very good at drawing either one of these, honestly. It's something like this. It goes on and on, right? And somehow you have the intersection of these two things, right?
Sort of a wedge cut out of your parabola perpendicular to the direction of the parabola open.
Yeah, maybe. So if I mean, I could look at it something like, from the top down, it looks like this. All right. From the side, it looks like this. Sort of. So this is actually, let's see here, let me try to be a little bit more precise here. This would be the y-axis. This would be the z-axis, all right? And so the x-axis is coming out at you here. This is not in the yz plane. This, I mean, you have to kind of envision it. Let's see, the best three-dimensional picture I can attempt here is something like, but that's just the positive. I won't try to draw both. That's the upper half of it. I do bad if I try to draw both halves of it once. So like this right here is part of, this is y equals x, right? This right here is what? This is y equals what? Y equals 4, z equals 0, x is free. That is this on this picture, right? And every one of, I mean, maybe I shouldn't draw those like this. Maybe it's better to, I'm not sure what's the most honest way to draw this picture, but these profiles, curves, are what? Every one of these is like a parabola, one of these kind of things, right? Oh, that's true. I could be, yeah, if that would be a way to make my picture even more precise. He's saying I should maybe even set my sights lower and just try to graph a quarter of it. Well, that would make it a much more fair test question, right? If I asked for just a volume of a quarter of this, then all of a sudden it becomes more manageable, doesn't it? So that right there, that would be the quarter. It would just be, yeah. But I hope you can see, despite the limitations of my graphing here, that this would be the projection of this solid t onto the xy plane, right? What you're looking at here is omega xy of t. This shape right here would be the projection of the solid onto what? Onto the yz plane, right? What would the projection on? There's one remaining projection left to think about, right? Which would be what? Right. I'll draw it like this just to be weird. What do you get? It's a diamond? Yeah, because that's, well, I mean, right. I think that the y equals, what's that?
Like sort of like a curving diamond.
A curving diamond. So we all see the point z equals plus or minus 2, yeah. And we all see that these points here, star and Pac-Man, those will project to here, right? Those are the extreme points on the x-axis. Where are those? What is star actually? For what? 440. Do we agree or disagree with that, folks? Y equals x. It's good. Z equals 0. Yeah, I'm on board. Now, why do you know it's 4 though? Because what's this point right here? Y equals that's 0, 4, 0, right? Which I know from this equation. When y equals 0, or rather when z equals 0, y equals 4. So yeah, I think I'll agree. So it goes 4 to minus 4, is that right? Now, how do I figure out these profile curves? Now, some of you said it's a diamond. Some of you said it's a curved diamond. How do we decide what those actually are? To me, the safest way is to actually find a parameterization of the curve. Let's maybe draw it in brown for a second here. What is this curve? If you want to be parameterize it, what would it be? We could use what as a parameter? Maybe lowercase t? Okay, I was going to say x, but... So I'm going to set x equals to t. How about that? Is that reasonable? Sort of. I mean, it's reasonable, but x is doubling up, right? Maybe z is a better choice for the parameter. Because this, I've only drawn half of it, right? It also does that. I can't draw the... I can't draw the other half of it at the same time. It's outside my skill set. But if I use x as a parameter, what's this? Is x? What's y? It's on the plane y equals x, right? So it's x again. What's z? It's at the intersection of the y equals absolute value of x, right? Or y equals x plane in this case, and y equals 4 minus, see, so that gives me plus or minus the square root, right? So at the moment, the top curve would be the square root of 4 minus x, right? Now, what's the projection? This projects to what? The projection onto the, xc. We said xc, right? Yeah. Sorry, I need to write it. The xz, what is the projection onto the xz plane? What does it kill? It just sets the y component to 0, right? And it keeps the x and the z components as they were. So this projects to x 0 square root of 4 minus x. Actually plus or minus, depending on whether you're on the upper part or the bottom part, right? So what do we have? We have z is equal to plus or minus the square root of 4 minus x for those profile curves. And so you guys are right, it was a curved diamond. In fact, those are what? Those are actually z squared equals to what? 4 minus x. So x is equal to 4 minus z squared, looks like. Yeah. So that was, exactly. So we probably could have figured that out easier if we just thought about it more clearly, right? But I'm just saying, if you don't have a clear mind, you can work through it bit by bit using parameterization ideas and so forth. But what do we have here? Just this, right? And then the other, how do I get the other side? Negative, right? Is it the So the difference would be that on the other side, the other side of this, you have y equals minus x, right? And so when you look at, when you look at, so that means when you look at y is equal to 4 minus z squared, that becomes minus x is equal to 4 minus z squared, which gives you that z squared is equal to 4 plus x, right? And so that's why you have this on the other side. It is a curved diamond. Yeah, I agree. With these in hand, we can easily write down the integrals in any order we like. So you guys pick an order, and we'll see if we can't use what we've worked out to derive the integral. Well, here, I'll do a function. I'm not going to actually do the integral, but so what order do you want to do the calculation in? YZX. Okay, so this makes y the most complicated integral, right? So that means these are the things we're doing last. We're going to want to look at the projection onto the ZX plane. All right? So that would be this thing. So first of all, how do I, what is the upper and lower bounds for y? If you look at this shape and you imagine it hits one thing on one side and another thing on the other, what is it? Y is between what and what? 0 would imply that, but no, I need the most complicated bounds. We have to, in terms of z and x, most precisely as we can be. I do the easy part. Y is equal to 4 minus z squared. That's as far out as you go. That's the paraboloid, the parabolic cylinder. That gives us the one edge. Yeah, yeah. So I would have absolute value of x to 4 minus z squared. And then, since you guys gave me zx, that means I need to make my x bounds go from minus 4 to 4, right? Because that's what x does. It goes from minus 4 to 4. And then how about z? I mean, how about the dz? What's z go between here? See, now you guys have caused me problems. We gotta have to do. Now let's see. This is an unfortunate event. We have to do 0 to 4 plus the integral. It's good that this happened. Minus 4 to 0. See why we have to do this? Because there's not the same top and the bottom here as there is over here. The profile curves that bound z as a function of x are different on the left and the right of the shape. So I have to break it into two integrals, the one going from 0 to 4 and the other one going from minus 4 to 0. Now, the story for the x and the y, well, the story for the x and the x is the only thing that remains the same. It's always that the cylinder, the parabolic cylinder is the top, and the y equals absolute value of x is the bottom. All right. Okay, so here, what's the top curve? And the bottom is. So for that reason, I put minus the square root of 4 minus x here, and plus the square root of 4 minus x there. On the flip side, on the other side, between 0 and 4, over here, on the top I have z is equal to the square root of 4 plus x. And down here I have z is equal to minus the square root of 4 plus x. And so I have to put minus the square root of 4 plus x here, and plus the square root of 4 plus x over there. Yep.
So because of the way that you think about the axis, the best term to last for integration into your y term when you only have to go from 0 to 4?
Let's see here. Let's just go for it. If we were going to do the integral f of x, y, z, I think I agree with what you just said. I'm just going to say, if I say dy, dx, dz, it makes it much easier. See, because the y bound stays the same. We're still dealing with the projection of the solid onto the zx plane, but now you see, if you look at this in terms of z being the outside, well, z goes between minus 2 and 2, right? And the cool thing is, if you look at horizontal, right, if you look at the horizontal slices here, or just like this, just draw a typical horizontal line, you see that there's a clear left and right, and it's given by the same equation from the top to the bottom. From the top to the bottom, you have x is equal to what? 4 minus z squared is the top, right? Wait a minute. Oh, what? Sorry, just a second. What's the red curve here? It is what? Well, it's right there, right? It's x equals to 4 minus z squared. And the green curve is x is equal to 4 plus z squared, right? Oh, no, not. What is this one? This one is x is equal to z squared minus 4, right? If I solve this, I get that, right? Yeah. So z squared minus 4 is the smallest x can be, and 4 minus z squared. So, yeah. But yeah, that would be easier because, yeah, you don't have to break it up into two pieces. In other words, that region, if we think of x and z as sort of being just the fundamental variables, is a two-dimensional problem where x plays the usual role of x and z plays the usual role of y, that region is type 2, but it's not type 1. It's the union of two type 1 regions. So if I do a type 1 integral, I have to break it up into two pieces to get the net integral. So anyway, I hope you see that there is a problem with these problems it's not something I can make go away. When you're asked to describe solids bounded by surfaces, you got to just keep drawing pictures until you understand what they are. And I think useful things you can do is to look at how do they intersect the coordinate planes, right? If you really wrestle with that and look at where they intersect, you can piece it back together if you spend enough time on it. They're not easy, and they take time, in my opinion. If you're more geometric than I am, you might be able to just see it from the start, right? But I hope I've provided you a little bit clearer path through the wilderness here. Pick a dimension that you don't like, project it out, and then look at the corresponding two-dimensional problem. This, of course, assumes that your solid has a simple enough shape that that makes sense. There are counterexamples to this. Yes? Yeah. Right. So the difference, all right, so the first one, we're looking at we're trying to write z, trying to bound z between two things, right? So when you look at this picture, that means we're trying to find a top and a bottom for a typical point, right? So I look at this point, the top is given by, the most it can be is the square root of 4 minus x. The smallest it could be is square root of 4 minus the square root of 4 minus x. But then when I'm over here, which is still in the region, all of a sudden the top is square root of 4 plus x, and the bottom is minus the square root of 4 plus x, but these are different functions, right? So I have to break it up into this piece plus that piece, because I don't have the same top and the same bottom across the whole region. Right, this one works because I have the same left function across the whole region, and I have the same right function across the whole region. In other words, this is a type 2 region, but it's not in its entirety a type 1. If I break it into just this piece, it's type 1 because there's a clearly defined top and bottom. If I just look at the right piece, it's a type 1 because there's a clearly defined top and bottom. But to actually do the two-dimensional integrals, we have to break it down into a union of type 1 and type 2 pieces, each of which we do the iterated integral over. Yeah.
Could you identify the fact that they were symmetrical and then just multiply one of those by 2?
Now that depends on the nature of the integrand. If this is also symmetrical, then perhaps. But beware that you need also the symmetry of the integrand function if you're going to do kind of doubling tricks. But yeah, we will. If we can get away with it, we will. Absolutely. Go for it if there's but do be correct. Yeah. I'm not so malevolent as to try to get you to prove that symmetries exist and are meaningful. I just let you use them. But I do have this insistence that you use them correctly. It's a good middle ground for a non-proof space course, right? I mean, yeah, I had a bad feeling when I was driving home the other day, and I called my brother up. I'm like, yeah, I was doing integrals today, and I like this example I did, blah, blah, blah. And he's like, yeah, I do it exactly the opposite way. And I was like, oh. See, Bill doesn't teach as much as I do, so all he does is sit around and think about how to make his course better. So I know whatever he's come to as an algorithm is optimal, right? So if pick a dimension, project it out, and then do the double integral is how he does it, that is the better way to do it. So and you can see it is. brother's so annoying.
And you're useful.
What's that?
And you're useful.
Yes, yes. We should use my brother whenever we can. That is true. Appalachian? So, with that, let us go on to the next topic. As doing another one of these triple integrals today will break my brain. Suppose you wanted to integrate over some region R the square root of x squared plus y squared dA. Or, well, yeah. Forget this. I mean, it could be that, but let's just think of a function of x, y. But suppose the region looks something like this. Sadness. All right. By now I should learn. You draw the axes last. All right. So it's like a pizza pie, but somebody got there first, right? The point is, this region is something like there's an outer radius, right? And then there's an inner radius. But they're both possibly functions of theta, right? F1 of theta, F2 of theta. I guess for my picture, well, if I'd drawn it better, maybe you'd think F2 of theta is just a constant function. I mean, sometimes that'll be the case. And so this is the region. And we're going from, say, theta 1 over here to theta 2. Now, if you think about how to do this integral, right, if you try to do this integral in Cartesian coordinates, my goodness, well, that would just be unpleasant, wouldn't it? Think about all the type 1 and type 2 regions you'd have to chop this into. At least 2, right? Like, I don't know, you could start parsing it into pieces, each one of which was type 1 or type 2, so you can find a clearly defined top or bottom or left and right function and chop it into pieces and integrate up, but there's got to be a better way, right? In fact, there is. We can do an integral with respect to polar coordinates, right? Let me describe to you how that goes. So the idea essentially is just, let's go back to basics and think about parsing this up into a bunch of subregions. So it's something like this. Right, so you might look at this typical subregion right here, where I'm going to blow it up. So you'd have a particular point in there that you could get, f of, say, x bar, I, y bar, j. That would be the, you could look at this. Imagine, make it three-dimensional. Imagine doing a stack of the integral, a stack of the volumes of like this. You have to add up the volume of each piece. But what would the volume of such a box be? So I mean, let me draw the picture here in 3 dimensions. What we're doing. Oh, I can't draw it worth anything. My point is that if we...
Just the R with non-cross-section.
You can look at these little sort of sector-based skyscrapers. So instead of taking rectangular skyscrapers, we could take skyscrapers whose cross-sectional area is like it's bounded between 2 circles and 2 rays, right? But if we take it small enough, they roughly speaking look like this. What What's the area of such a sector? It depends on two things, right? Basically, what's the distance from the origin out to here, which we call r, right? So this distance, we would call the change in r, right? What's this length here? Well, let's just kind of take it through the middle. I suppose this would be r, this would be r plus delta r, right? So, I mean, roughly speaking, if we let delta r go to 0, it doesn't really matter where we measure the radius from. To a crude approximation, though, the area of this is something like what? It's something like, this arc length is what? It's something like r delta theta, right? So then to get the volume of this, I would do this times r delta theta times delta r, basically, right? And then I just have to basically let the number of these subdivisions go to infinity and add these up. So what happens then is we'd end up getting this, that this is in fact equal to, and sorry, I could be a little bit more careful, but I don't think there's much harm in the sloppiness of what I've just done. Theta 1 to theta 2, and the r bounds go from f1 of theta to f2 of theta. And you notice there's an interesting thing here, that we've picked up this r factor, right? Because the area of the typical approximating region gets scaled according to how far away it is from the origin in this choice of coordinates. So we pick up this r factor, and so f, what do? You do f of r cosine theta, r sine theta, that's y and x, right? And then we do r. Now which comes first, dr or d theta? Am I set up? dr d theta, right? And there you go. This right here, folks, is the theorem, if you like, which I have certainly not proved, but I've sketched the proof of. That is how you calculate integrals using polar coordinates. You notice that there's this seemingly ad hoc introduction of this factor of r here. Don't forget it. It's important.
If you drop it, your scale goes.
Yeah, if you don't do that, you're wrong. Yeah. Yeah, the 1 over r in the gradient formula is very much related to this. Yeah. Okay, so do I have 5 minutes? 2 minutes. How many? 3 minutes. All right. I need a 3-minute example. Here's one. So remember we calculated the centroid of the quarter circle the other day, right? So we had to integrate basically x dA, and we had to integrate y dA over this region. How to describe this region in polar coordinates? 0 less than theta less than pi over 2. R in is 0. R out is 1 if it's a unit circle, right? So if I want to integrate x dA over this region, what I do is I integrate from 0 to 1, integrate from 0 to pi over 2. X is what? In terms of polar coordinates, x is what? Right, r cosine theta. And what was the dA basically? I mean, one way you can think of it is this is dA in polar coordinates. What's dA in Cartesian coordinates? It's dx dy, right? So this is r dr, wait a minute, r d theta dr in my current. Oh, I didn't think it was that bad. But let's see here. So this actually is multipliable, right? So you can do r squared dr from 0 to 1, integrate from 0 to pi over 2, cosine theta d theta. What do we get? Oh, just sine theta, right? One-third. Now that's not the center. I mean, we also had to divide by the, what did we do? We divided by the, is that what we got? I don't know. I can't remember now. But anyway, here's an example of an integral that you can do. That would have been a drag in Cartesian variables, right? If we were using Cartesian coordinates, I'd had to look at the integral. One of the integrals, we would have faced a square root. No square root, right? Anyway, we'll do more of these tomorrow. Thanks, guys.